Imagine standing outside on a clear night. You look up at the stars and the vast darkness, but why is that sky dark? It's one of the deepest mysteries in physics. Most think it's just because the sun has set. But if the universe is infinite and filled with stars, every line of sight should eventually hit one. If stars are everywhere, the sky should be as bright as the surface of a star. To understand why it isn't, think of a forest. In an infinite forest, every direction you look hits a tree. Replace those trees with stars, and the sky should be a solid wall of light. But it's not. It's black. This clue tells us something profound about the age and expansion of our universe. Stay curious. Subscribe for more mysteries of the universe. Why do you think the sky is dark? Let us know. But somewhere far away in the depths of space, that line of sight must end at the surface of a burning star. And if that is true, then something extraordinary should happen. Every direction in the sky should glow. Every point in the sky should eventually connect to a star. That means the entire dome above your head should be filled with light. Not just scattered points of brightness, but a continuous sheet of light covering the entire sky. In fact, the brightness should be overwhelming. If the universe were truly infinite and filled with stars forever, the sky would not be dark at night. It would shine with roughly the same brightness as the surface of the sun itself. The entire sky would blaze with light. Oceans would boil. The earth would be heated to unimaginable temperatures. Life as we know it would be impossible. But when you step outside tonight and look up, that is not what you see. You see darkness. You see a handful of tiny points of light scattered across an enormous black background. This contradiction is not just an interesting observation. It is one of the most famous puzzles in cosmology. Scientists call it Olbers Paradox, a problem that has troubled astronomers for centuries. Thinkers like Kepler and Halley wrestled with it long before modern cosmology existed. The paradox is simple but powerful. If the universe is infinite, eternal, and filled with stars everywhere, the night sky should be brilliantly bright, but it is not. The darkness itself is evidence that something about our assumptions must be wrong. Nature is trying to tell us something. The blackness of the night sky is not an accident. It is a message. It is a clue that the universe is not infinite and unchanging in the way people once believed. And once scientists began following that clue, it led them to one of the most profound discoveries in the history of science. To understand the real answer, we have to rethink everything we thought we knew about space, time, and the history of the universe itself. Now, at this point, many people feel uncomfortable with this conclusion, so naturally the mind begins searching for an escape. Perhaps you think the distant stars are simply too faint to matter. Maybe their light becomes so weak across enormous distances that it disappears. This sounds reasonable. If you hold a candle right in front of your face, it is bright. But if you carry it far away, eventually the flame becomes too dim to see. The same must happen with stars, right? The stars that are incredibly far away should become so faint that their light contributes almost nothing. Physics, however, forces us to examine that intuition carefully. There is a well-known rule in physics called the inverse square law. This law describes exactly how the brightness of light changes with distance. When a light source moves farther away, its brightness fades according to the square of the distance. Twice as far means 4 times dimmer. If stars become dramatically dimmer as they move farther away, their faint glow should eventually vanish into darkness. But space is 3-dimensional, and that simple fact completely changes the calculation. Imagine the Earth at the center of enormous spherical shells. Each shell represents a region of space at a specific distance. The surface area of a sphere grows with the square of the radius. If you double the distance, the area becomes 4 times larger. That means a shell twice as far away contains 4 times as many stars, assuming they are evenly distributed. Each star is 4 times dimmer, but there are 4 times as many stars. The total light remains exactly the same, and the same logic continues throughout the infinite reaches of space. In an infinite universe filled with stars, every direction we look should eventually land on the surface of a star. The night sky would look like a continuous glowing wall of starlight, thousands of degrees hot. Earth would be bathed in constant blazing radiation, yet the sky we see is dark and cold. This contradiction tells us that one of our assumptions about the universe must be wrong. For a long time, astronomers thought enormous clouds of dust floating in space blocked the light, like fog on a road. The idea makes sense, like driving through fog where distant lights disappear from view. But physics has a rule that refuses to allow such an easy escape. This rule is the conservation of energy. It states that energy cannot simply vanish, it can only change form. Now think about what happens when light from a distant star strikes a grain of cosmic dust. The photon carries energy as it travels through the vastness of space. If the dust particle absorbs that light, the energy must go somewhere. It cannot disappear. Instead, it heats the dust particle. And when objects become hot, they do something very familiar. They glow. Consider a piece of iron placed inside a blacksmith's furnace. At first it is dark, but as it absorbs heat from the fire, its temperature rises. Soon the metal begins to glow red. As it gets hotter, it glows orange. Eventually it shines white hot. This happens because the iron is releasing the energy it absorbed. The same thing would occur with cosmic dust. If the universe were infinite and filled with stars shining from every direction, dust particles floating in space would constantly absorb enormous amounts of starlight. Over millions or billions of years, they would heat up more and more. Eventually, the dust would reach a temperature where it radiates just as much energy as it absorbs. At that point, the dust itself would begin glowing brightly. So even if dust blocked the distant stars, it would not solve the paradox. Instead of seeing a sky filled with stars, we would see a sky filled with glowing dust clouds. The result would be the same. The sky would still be blazing with light. Trying to hide the starlight behind dust would be like trying to block the sun with a blanket. The blanket would absorb the sunlight, heat up, and begin glowing just as brightly. The heat and energy cannot disappear, so the dust explanation fails completely. We cannot hide the light. The geometry of space says the light must be there. The laws of thermodynamics say the energy cannot vanish, and yet when we look up at the sky, we still see darkness. By this point, the puzzle becomes impossible to ignore. The universe is clearly not behaving the way our original assumptions predicted. If the sky is dark, then something fundamental about the structure of the universe must be different from what astronomers once believed. The question now becomes much deeper. Is the universe not infinite? Is something happening to the light as it travels through space? Or could the real answer involve something even stranger, something connected not just to space, but to time itself? Once the dust explanation collapses, the problem becomes much more serious. We can no longer hide the light behind clouds of cosmic particles. The geometry of the universe still demands that every direction should eventually end on the surface of a star. Yet observation stubbornly tells us the opposite. The sky is mostly empty and dark. At this point, scientists began searching for another escape. Maybe the mistake lies not in the light or in the dust, but in the way stars are arranged throughout space. In our earlier reasoning, we quietly assumed something very specific, that stars are spread out fairly evenly across the universe. We imagined them distributed like raisins scattered through a pudding or butter spread smoothly across bread. But when we actually look at the sky, we know the universe does not appear perfectly uniform at smaller scales. Stars gather into solar systems. Solar systems gather into galaxies. Galaxies cluster together into enormous groups. Between those clusters lie vast regions of almost empty space. So perhaps some scientists suggested the universe is not evenly filled with stars at all. Maybe the structure of the universe becomes more and more empty as we look farther out. Perhaps the stars form patterns that repeat on different scales, with larger and larger gaps appearing between them. Mathematicians call this kind of structure a fractal. If the universe were fractal in this way, the earlier calculation might change dramatically. Remember that our paradox depended on adding up equal amounts of light from each spherical shell surrounding Earth. But what if the shells farther away contained fewer stars instead of more? If the density of stars dropped rapidly enough with distance, then each shell might contribute less light than the previous one. Instead of adding up equal amounts of brightness, 1 plus 1 plus 1 plus 1 forever, we might be adding something like 1 plus 1 half plus 1 quarter plus 1 eighth. A series like that does not grow without limit. It approaches a small finite value. In other words, if the universe becomes emptier and emptier at larger distances, the sky could remain dark simply because there are not enough stars far away to fill it with light. For a time, this idea seemed very promising. A Swedish astronomer named Carl Charlier explored this possibility in detail more than a century ago. Mathematically, the fractal universe solved the paradox beautifully. The equations worked perfectly. If the universe had that type of structure, the night sky could remain dark without violating the laws of physics. But science does not stop with elegant mathematics. Ideas must survive confrontation with observation. Over the last several decades, astronomers have mapped the universe in extraordinary detail. Using powerful telescopes and large sky surveys, they counted galaxies and measured their positions across enormous regions of space. These observations allowed scientists to build three-dimensional maps of the cosmos, stretching billions of light years in every direction. Why is the night sky dark? If the universe were infinite and eternal, the entire sky should blaze with starlight. But on the largest scales, the universe is uniform. This leads to a trap known as the dark sky paradox. The solution? The universe had a beginning. Light from the most distant regions simply hasn't reached us yet. Writer Edgar Allan Poe proposed this in 1848, long before modern cosmology confirmed it. Looking into space is looking back in time. At 13.8 billion years old, the universe has a visible horizon. Anything farther away is too distant for its light to have arrived. The darkness is proof of our beginning. Picture yourself standing in a forest again, but this time imagine that you woke up there only 10 minutes ago. Light travels slowly through the forest, perhaps at the speed of a walking person. When you look around, you can see trees that are close by. You can also see trees a few minutes away because their light has had enough time to reach you. But trees that are extremely far away remain invisible. Their light is still traveling through the forest, slowly approaching but not yet arrived. So instead of seeing a solid wall of trees, you see gaps between them. Those gaps are not empty forest. They are simply regions whose light has not reached you yet. The same principle applies to the universe. When we look into space, we can only see the stars and galaxies whose light has had enough time to travel across the cosmos and arrive at Earth since the beginning of the universe. Beyond that distance lies a boundary known as the observable universe. Outside that boundary, there may be more stars, more galaxies, perhaps even infinitely many of them. But their light is still on its journey. For us tonight, it has not arrived yet. This idea resolves the paradox beautifully. The sky is dark, not because the universe lacks stars, but because the universe is young. Light from the most distant stars simply has not had enough time to reach our eyes. But even that explanation is not the whole story, because the universe is not just young, it is also expanding. Once we realize that the universe had a beginning, the mystery of the dark sky begins to make sense. But there is another discovery that makes the explanation even deeper and more fascinating. The universe is not simply sitting there quietly aging, it is expanding. This idea was first confirmed in the 1920s by the astronomer Edwin Hubble. When he carefully studied distant galaxies, he noticed something remarkable. Almost every galaxy he observed appeared to be moving away from us, and the farther away a galaxy was, the faster it seemed to be receding. This observation revealed something extraordinary about the nature of space itself. The universe is not a fixed stage where galaxies move around like actors on a motionless platform. Instead, the stage itself is stretching. The fabric of space is expanding in every direction. Once you understand this expansion, you must ask a new question. What happens to light when it travels through space that is stretching while it moves? To answer that, think about a simple example involving sound. Imagine standing beside a road as an ambulance drives past you. When the ambulance approaches, the sound of the siren has a higher pitch. As the vehicle passes and begins moving away, the pitch suddenly drops to a lower tone. This change in pitch occurs because the sound waves are being compressed when the source moves toward you and stretched when it moves away. Scientists call this effect the Doppler effect. Light behaves in a similar way because light is also a wave. Instead of sound waves in air, light consists of electromagnetic waves traveling through space. These waves have different wavelengths, and those wavelengths determine the color we see. Shorter wavelengths correspond to blue light, which carries more energy. Longer wavelengths correspond to red light, which carries less energy. When a star or galaxy moves away from us, the waves of light it emits become stretched. Their wavelength grows longer, shifting the color toward the red end of the spectrum. This phenomenon is known as redshift. In an expanding universe, the effect becomes even more dramatic. It is not just the galaxies move through space like cars on a road. The space between galaxies itself is stretching. As light travels through this expanding space, the wavelengths of the light stretch along with it. Imagine drawing a wavy line across a rubber band. That wavy line represents a beam of light. Now pull the ends of the rubber band apart. As the rubber stretches, the waves drawn on it become longer and more spread out. And that's the core of the mystery. The universe isn't just young, it's also growing, stretching the very light that tries to reach us. Next time you look up at the dark sky, remember that you're looking at a universe still in its infancy, reaching out across the void. The ink remains on the rubber band, but the shape of the wave changes. The same thing happens to light traveling through the expanding universe. A photon might begin its journey billions of years ago as bright visible light, but as it travels across the expanding cosmos, the wavelength gradually stretches more and more. Eventually, the light becomes so stretched that it moves beyond the range visible to human eyes. What started as visible light may shift into infrared radiation or even into microwave radiation. Our eyes cannot detect those wavelengths. So when we look toward distant regions of the universe, some of the light reaching us is simply invisible to our eyes. The energy has been diluted by the expansion of space. This means the night sky remains dark for two major reasons. First, the universe has a finite age. The most distant light has not yet had enough time to reach us. Second, the expansion of the universe stretches the light that does arrive, reducing its energy and shifting much of it beyond the visible spectrum. But here is the most astonishing part of the story. Even though our eyes see darkness, the sky is not truly empty. In fact, every direction in the sky is filled with radiation left over from the birth of the universe itself. To understand this, we have to go back to the earliest moments after the Big Bang. When the universe first formed, it was unimaginably hot and dense. The entire cosmos was filled with a glowing sea of energy and particles. For hundreds of thousands of years, the universe was so hot that light could not travel freely. Photons constantly collided with charged particles in a dense plasma, making the universe opaque like a thick fog. Eventually, about 380,000 years after the Big Bang, the universe cooled enough for atoms to form. When that happened, the fog cleared and light was suddenly able to travel freely through space. That ancient light has been traveling across the universe ever since. As the universe expanded over billions of years, the wavelengths of that radiation stretched enormously. What was once brilliant visible light has been transformed into microwave radiation. This radiation fills the entire sky. It is known as the cosmic microwave background. Scientists first detected it in 1964 when two researchers, Arno Penzias and Robert Wilson, were working with a large radio antenna. They kept hearing a faint hiss of noise that appeared no matter where they pointed the instrument. At first, they thought it might be interference or even pigeon droppings inside the antenna. But after careful investigation, they realized the signal was coming from everywhere in the sky. They had accidentally discovered the faint echo of the Big Bang itself. If our eyes were sensitive to microwave radiation, instead of visible light, the night sky would not appear dark at all. It would glow uniformly in every direction, revealing the ancient heat left behind from the birth of the universe. In other words, the sky is not truly black. It only appears dark because human eyes are blind to most of the radiation filling the cosmos. So when you step outside tonight and look up at the stars, remember that the darkness above you is not simply empty space. It is a window into the history of the universe. The dark gaps between the stars are not just voids. They represent regions where the light from distant galaxies has not yet arrived, or where ancient radiation has been stretched. The night sky is dark because the universe had a beginning, because space itself continues to expand, and because much of the cosmic light around us lies outside the range our eyes can detect. A simple question, why is the sky dark, leads directly to the deepest truths about the origin, age, and evolution of the universe.